Okay, good morning, everybody.
Good morning, sir.
Good
So,
morning, sir.
yesterday I was discussing with you uh, eigenvectors, if you remember, and a matrix like this was there. A is equal to -2, 2, and -3, and 2, 1, -6, and -1, -2, and 0. Okay. So this type of matrix was there, and we calculated the eigenvalues uh, 5, -3, and -3, and corresponding to 5, I wrote an eigenvector corresponding to 5, and what was that? For lambda is equal to 5, it was 1, 2, and -1. Correct? 1, 2, and -1. Now, corresponding to this, lambda is equal to -3. If you try to write the eigenvectors, so you will find that what will be the matrix, what it will become. So it will
1,
become
2,
-2, 1,
1,
2,
-3,
-3,
2,
2,
4,
4,
-6,
-6,
-1,
-1,
-2,
-2, and 3.
3.
Okay, this will be the matrix, and then eigenvector. Let's take it x1, x2, x3, and this will be equal to 0, 0, and 0. Now you can see the pattern in this, that these all three rows are same. Can you see that? This row, this row, this row, all are same. This is 1, 2, -3 divided by 2. What it will become? 1, 2, -3. And take minus common. What it will become? 1, 2,
1, 2,
-3.
-3.
So all
So,
three rows are same. So you can just subtract them, and by elementary row transformation, you will get 1, 2, -3, 0, 0, 0, and 0, 0, 0, and as an eigenvector x1, x2, x3, and this side also 0, 0, 0. So if you write the equation, what it will become? If you write the equation, it will become x1 plus 2x2 and minus 3x3. This will become equal to 0. So this equation will become x1 plus 2x2 minus 3x3 is equal to 0. And now you have only one equation that you have to use to write the vector. So that means we have to, write we have to assign two different values. So for example, I will write this x1 as some k1, x2 as some k2, because three variables are there and one equation is there. So this is the only way to solve that. You have to assign two different values. So it will become k1, k2, and what will be the value of this x3? It will become 1 by 3 k1 plus 2 times K2. Okay. So now corresponding to lambda minus 3, the first eigenvector I can write is 1 and 0. If I assign it as 1, and the second vector k2 I assign 0, so it will become 1 by 3. Can you see that? So that means it will become 3, 0 and 1. This will be the first eigenvector that you will get. You can normalize it also. And you have another lambda is equal to minus 3, which will give the same equation.
Sir, how K2 is 0?
Sorry?
Please. Sir, K2 0. ये समझ नहीं आया सर.
इसमें समझना क्या है? बताओ भाई. What do you want?
Sir, K1 is equal to 1.
हाँ, ये कैसे है? ये कैसे है?
नहीं सर, वो तो हमने लेट कर लिया.
तो ये भी
K2
लेट ही है. जब दो
Okay.
लेट करोगे तभी तो तीसरा निकलेगा, जब एक ही इक्वेशन है.
Okay, sir.
You have only one equation ना, तो how you will solve? You will have to assume 2 and then you will get the third value. Third you can't assume.
Thank you, sir. Okay.
So any two values you will assume and third you will get. So this is one vector and another vector corresponding to same. Please understand this point very carefully. So you should write the linearly independent vector. So suppose this is corresponding to lambda is equal to minus 3 and there are degenerate values. So this may represent another vector. So corresponding to this, here I took 1 0. So this time I will took 0 1. So that they are always linearly independent. Because if one value here is non-zero and here it is 0, they can be never written in the form of one another. Correct? So you take it as 0 and take it as 1. What you will get here? 2 by 3? सही है ना? So if you multiply it by 3, the vector will be 0, 3 and 2. So these are two linearly independent vectors. And similarly you can write other vectors also. कोई बताएगा? एक other vector लिख के दिखाओ. So this time let us take k3 is equal to 0. Correct? Suppose I take k3 is equal to 0 and second one x2 is equal to 1, then what will be the value of x1? Minus 2. So this is another vector. Please see. Same equation. Equation remains same. Tell me, are you able to understand this? Everybody? This everybody understood or not?
Yes, sir.
So you got an idea. You can write another ways, other vectors also. So please, why this is important, that when options are given, you should know that how to write it, because maybe you calculated this and option is this. So you will immediately realize that this is also same equation. This also follows the same equation and it can be written immediately. So this was very important part of your this eigenvalues and eigenvectors. Write a small note like thing here. The order m lambda of an eigenvalue lambda as a root of the characteristic polynomial as a root of a characteristic polynomial is called the algebraic multiplicity of lambda. Is called the So these terms should be clear. You already know that you write a characteristic equation. So order of that is known as multiplicity, is called the algebraic multiplicity of lambda. Okay. Next, the number m lambda of linearly independent eigenvectors the number m lambda of linearly independent eigenvectors linearly independent eigenvectors corresponding to lambda is called geometric multiplicity. Corresponding to lambda is called geometric multiplicity. Okay, it's called geometric multiplicity of lambda. So there is a possibility sometimes that you have, suppose here the order is 3, but you get only 2 linearly independent eigenvectors. Third you cannot write. तो ऐसा हो सकता है, ठीक है, in some cases. So that's why they may be different. M lambda is the dimension of eigenspace. इसको और क्या कहते हैं? Is the dimension of eigenspace. So just note down this. So in general, we can write that this m lambda, this will be less than or equal to capital M lambda. Okay. Is that okay? So same thing, the terms are defined. Baki to you understand that what I'm talking about. So just different names are there. So suppose you have a 3x3 matrix, then you have a polynomial, so that will have order 3, and then you calculate the linearly independent eigenvectors. So like in our case, the number of eigenvectors that we calculated, different linearly independent eigenvectors So we calculated that. So in every question, it will be asked that we can calculate this and we can also calculate this difference, and that is known as defect, positive defect, positive defect. So that is represented by some del lambda. Okay, so because this is greater, so m lambda, capital M lambda minus small m lambda will be known as defect. So I will solve one more question and we will just write these quantities there. Okay, so again I am giving you a matrix. Capital A is equal to 0, 1, 0, 0. Okay, suppose this is the matrix. Okay, so let us write the eigenvalues and eigenvectors quickly for this matrix. So how to write the eigenvalue? A minus lambda I is equal to, and into x some vector is equal to 0. This is the equation. So we'll form the characteristic equation by putting this is equal to 0. So what it will come? Batao bhai. 0 minus lambda 0, 1 and 0 minus lambda. Okay, and what you will get here putting this is equal to 0?
Lambda square equals to 0.
Lambda square is equal to 0 means lambda is equal to 0 comma 0. Lambda is equal to 0 comma 0. Correct? So let us calculate. So these are degenerate values or not?
Degenerate,
Degenerate, sir.
Degenerate. Now let us calculate the values here. So what will happen if you will write the vector? It will be like this: 0, 1, 0, 0, and the vector x1, x2 is equal to 0, 0. Okay.
Yes, sir.
And write the equation. Who will tell? 0 x1
Plus 1x2
1
1x2
x2
equals to 0.
equals to 0.
0x1 plus x2.
Correct? And the second equation, 0 x1
Plus 0
plus
x2.
0 x2 is equal to 0. So this will not solve any purpose. Only this will.
Yes, sir.
So if I take, so according to this 0 x1, according to this x2 is for sure 0. Yes. Tell me.
Yes,
Yes.
sir.
Yes,
or
sir.
no?
Yes, sir.
Yes, sir.
And if x2 is 0, can anybody tell me what will be the vector that will be formed? So my vector is this x1, x2. X vector
x1,
is,
comma 0.
so x1 is arbitrary.
Hmm.
So k comma 0. So if you put k is equal to 1, so it will be just 1 comma 0. This x1. Correct? Yes or no?
Yes, sir.
Now,
Yes, sir.
now question is, can I write one more linearly independent?
No, sir.
So what is the defect?
Because
What is the value of defect here? Jaldi, quickly. What is the value of defect? So what was the value of capital M here?
zero.
No, what is the value of capital
Two.
2?
Sir.
2.
2, and you got only one independent eigenvector because another you can't write. Whatever you will write will be linearly dependent. That will be just a multiplication of parallel vectors. Basically, you will only write parallel vectors. So this will be 2 minus 1 is equal to 1. Correct?
M lambda minus m small m lambda, that is del m lambda. So one lambda will be coming, or only one we have to mention.
One lambda will be coming. Yaar, lambda is that eigenvalue na, that is 0 I have written. वो तो just notation hai.
Okay.
It is just notation. When you write this is equal to m lambda, these are suffixes.
Okay, previously I mentioned that m lambda will multiply.
No, never I wrote like that. Please see. These are suffixes, na? This is a number. This is again a number. Okay. So can I erase this also?
Yes, sir.
Okay. So now I will be completely depending on you. I will write a matrix and immediately you calculate everything. The matrix capital A is equal to 3, 2, 0, 3. This is the matrix. चलो जल्दी से, quickly.
Three comma 3.
Yes.
Comma 3, sir.
So what is that?
Values of lambda.
So value of lambda is equal to 3 comma 3. So it is also doubly degenerate. And what are the values of eigenvectors?
1, 0.
A0.
So lambda is equal to 3. So how we will write the equation? 0, 2, 0, 0, and x1, x2 is equal to 0, 0. So you will have only one equation, 0x1 plus 2x2 is equal to 0. That means x2 is for sure 0 and
Yes, sir.
x1 can be arbitrary. Yes? x1 can be arbitrary. So again you will get the eigenvector as some k comma
0.
0. So this type of questions we should do. This was very simple, and let me now proceed. Can I erase this also? Everybody has done now?
Yes, sir.
Yes, sir.
Okay, so now let me just give you another question. A is equal to 0, 1, minus 1, 0. This is the matrix. And we have to find eigenvalues and eigenvectors. So what is A minus lambda I? What is F? F lambda is equal to 0. This will be the equation. And what is the value of lambda? Iota and minus
Yes,
I.
iota.
Okay. And please see what type of matrix is this? A transpose
Skew symmetric.
is equal to 0, 1, minus 1, 0. So that is minus of 0, 1, minus 1, 0. So this is skew symmetric. So that's why obviously the eigenvalues for a skew symmetric matrix are what? Imaginary. Eigenvalues for such a matrix are what type of values?
Imaginary values.
Imaginary values. Now we will calculate the eigenvectors corresponding to them. So the first eigenvector I will calculate corresponding to lambda is equal to iota. So it will become minus iota 1 minus 1 minus iota into x1 x2 is equal to 0 0. Okay. Now what will happen?
Minus x1.
Minus iota x1 plus x2 is equal to 0 and
Minus
minus
x1
x1
minus I x2 equal to 0.
is equal to 0. So now please see this. If I just multiply it by negative sign and then iota, are these two equations same or different? So suppose I multiply this by iota. Let's see what happens. Iota x1 and plus x2 is equal to 0. So same equation is there, na? So minus iota x1 is equal to minus x2, correct? So that means this is the equation. So if I write the equation like this, so let me take x1 as 1. So what will be the value of x2? X2 will become iota.
Iota.
Okay. So this will become x1. If x1 is 1, then x2 will become iota. It's okay. What is problem? If x1 is 1,
Yes, sir. Correct, sir.
that is okay.
Yes, sir.
किसको प्रॉब्लम है भाई? This is okay, I think. And next is corresponding to the second one. So I will just and its normalization will be √2. So if you take minus iota, then what will happen? This time it will become iota and iota 1 minus 1 x1 x2 is equal to 0. So it will become iota x1 plus x2 is equal to 0 and minus x1 plus iota x2 is equal to 0. Correct? So these two equations are also same. Iota x1 is equal to minus of x2. So if you write the equation in which x1 is 1, x2 will become minus iota. This will become the vector. Okay?
Sir, if we consider the second equation, we will get another vector, no, sir?
So second equation is same, na? Both equations are same.
But x1 is equal to I x2 will come, no, sir?
X1
Positive.
So those two things are same. Those two things are not different.
Okay, sir.
So here also, if you consider x1 as 1, x2 will be minus iota. Where is the difference? Okay?
नॉर्मलाइज्ड कांस्टेंट क्या आएगा इसमें?
1 by √2.
One by √2.
In the starting, you had told that lambda has to be a proper value. What
Lambda has to be a
proper value?
no. I have not told that lambda has to be a proper value. I have told the meaning of eigenvalue is proper.
Okay.
When we say eigenvalue, it means proper value. That is literal meaning of eigen.
Okay, sir.
So write as a note one important point that A and A transpose have same eigenvalue. Have same eigenvalue. Okay? If you write A and A transpose, both will get the same eigenvalue. Now, I discussed with you about the symmetric, skew-symmetric and orthogonal matrices, and I told you regarding the properties of that, and you remember about the eigenvalues of symmetric matrix being real, Hermitian matrix being real, and skew-symmetric
Imaginary.
matrix imaginary or zero. Okay, and skew Hermitian also imaginary or zero. And the determinant value of orthogonal and unitary matrix is +1 and -1. So absolute value is always 1, na? absolute value will be always equal to 1. So the determinant value of, if you calculate the determinant value of orthogonal matrix, and what I told you about the eigenvalues of orthogonal and unitary matrix, they will always lie on the
unit circle.
That means their absolute value will be always 1.
Yes.
The meaning, because they will be complex, but
Lying on the
if you
circle.
see the absolute value of those complex numbers, that will be always 1 because they are lying on the unit circle. So these properties are very important, and write that also again regarding that. So now a very important concept comes, that is similarity transformation. So this is very important properties of the matrix, and it is known as similarity of matrices or diagonalization. Similarity of matrices or diagonalization. So how we define a similarity transformation? So consider we have a matrix A, which is n cross n, a square matrix, and A cap is suppose the similar matrix to A. Similar matrix to A. So A similar matrix is defined as P inverse A P. This is the definition of A cap, and P is the matrix which should be non-singular. Non-singular means its determinant value should not be equal to 0, formed by eigenvectors. Formed by eigenvectors of A. So suppose A is a matrix, you calculate the eigenvectors, put them in column, a matrix will be formed that will be known as P. But you know here P inverse is also there, which is inverse of the matrix. Inverse of matrix. And you know inverse of a matrix is defined as, suppose we define A inverse, it will be adjoint A over determinant A. So if determinant A is 0, then inverse is not defined. If the determinant value of A is 0, then the inverse is not defined. So that's why I am writing that P should be a non-singular matrix. Okay, so we will calculate the eigenvalues, and now write something about the A cap. A cap and A have same eigenvalues. Have same eigenvalues. A cap and A have same eigenvalues. And also, if X is suppose eigenvector of A, eigenvector of A, then Y is equal to P inverse X is eigenvector of A
Sir,
cap.
it's
So this is also a very important point, that if X is eigenvector of A, then Y is equal to P inverse X will be eigenvector of A cap corresponding to same eigenvalue. Corresponding to same eigenvalue. Same eigenvalue. So understand all these points. Main understanding will be done when we will solve a problem. So how to write this similarity transformation or diagonalization? You have A, please see this. You will write the eigenvalues, correct? This you know? Then you will write the eigenvectors, correct? This also you know? You will put them in the columns. That will be P matrix. P matrix is clear to everybody?
Yes, sir.
So put them in column, you will get P matrix. This is the method. So these things many times they asked. Language is such that if you don't understand all this especially, see, X is eigenvector of A, then Y is eigenvector of A cap by writing Y is equal to P inverse X.
Sir?
Hmm?
Sir, in the order in which we put the eigenvector columns.
That will not affect na, because you take P once, then don't change, because P inverse will be calculated using P.
Okay, sir.
Is that fine?
Yes.
And if we transform it suitably, this A cap may become a diagonal matrix. So write that line, write that sentence. By a suitable similarity transformation, by a suitable similarity transformation, by a suitable similarity transformation, A cap can be a diagonal matrix. A cap can be a diagonal matrix. A cap can be a diagonal matrix having, diagonal matrix में क्या होता है? So if you write a diagonal matrix, then only principal diagonal will have non-zero elements. कोई non-zero element होगा तो that will be only on the principal diagonal, all other elements will be zero. So suppose this is a diagonal matrix or not? Tell me.
no,
Yes,
sir.
No, yes, sir.
Yes,
Yes,
why,
Yes,
why no? Why no? Why no भाई बताओ ना, जल्दी बताओ.
You told principal diagonal non-zero.
So principal diagonal is non-zero, na? If any term is non-zero, that has to lie on principal diagonal. What is the problem? This
One
is
of them is zero, sir.
that is zero. It is okay. But I have मैंने क्या ये कहा कि zero नहीं हो सकता diagonal पे? मैंने ये बोला?
No.
I said that if any term is non-zero, that has to lie on the principal diagonal. Here we cannot have a non-zero term. Here we cannot have a non-zero term. Okay. So that matrix, that's why I gave that exceptional example in which one term was 0. Otherwise, I could have written it as this 1 1 0 0. This is also a diagonal matrix. Okay.
Yes, sir.
So diagonalization is kind of a special case of similarity transformation in which you select P suitably, and when you do the transformation, it becomes all elements only lie on the principal diagonal, and incidentally they are eigenvalues. They become the eigenvalues. So we can do many things with that. That I will take up in next class. Okay.